Hello everybody and welcome to my 8th session of the lecture on statistical energy analysis and hybrid methods. This time I will talk about reflection and transmission of plane waves. That is quite an academic problem, but anyhow it's a first hint on how acoustic wave fields are coupled between neighbored systems, in this case two areas of fluids. And you will learn what is the determining property, so which property defines the coupling of those different wave fields, and this is an important first step in SEA towards the coupling loss factor. So we start with a reflection arrangement. So we have an incoming wave with wave number K1. The media on the positive Z area is described by density and speed of sound of medium 1, which gives the impedance, the characteristic impedance 1. And we have a surface with property, the surface impedance Z2. In this upper solution, we have two plane waves. The first one is described by this vector potential given by this wave number and the argument of the upper space. And we have to add the reflected version of this to the total solution. These quite unhandy arguments of the wave number and the reflected wave number can be changed by using trigonometric functions, so that the exponential function is now described by sine and cosine functions and the related angles. This makes it much easier to find out what is the reflected angle compared to the incoming one. So to solve the issue, we need the boundary conditions, and this is given exactly here at the z equal to 0, which is the surface defined by. And for this, we need first the pressure at the surface, which is given for the z equals 0. And we use the potential, the vector potential functionality, which gives the pressure out of the vector potential, leading to this solution at the surface, obviously only dependent on x. Then, if we're interested in the velocity in z direction, as shown here, we have to use the vector, the potential again, and then we get this solution with those arguments here in the exponential function. The trick is now, if we would like to fulfill the impedance boundary condition, we have to do this at every surface area here along the dimension x, and the only option that this is possible is that the arguments in the exponential function are similar. So this is only possible when the incoming and outcoming angle is the same. So with this knowledge, we can calculate the impedance using the pressure and the velocity here, and then we get this solution for the impedance, and this is the expression that we get depending on the impedance on the upper area, the angle, and the incoming and reflected amplitude. So using that, we have in the upper area the characteristic impedance 1, and rearrange the upper equation, we can calculate the reflection factor out of this. Reflection factor is nothing else than the ratio of amplitudes reflected divided by the incoming amplitude, and then we get this expression. So please note that the reflection is just defined by the characteristic impedance of the fluid, and then this expression here mainly including the angle and the impedance of the surface. So when we are interested into the reflected power or power related quantity, we have to square this reflection factor, because then the amplitude is also squared, and this gives us an idea about what is the energy or the intensity component of this reflected acoustic waves. This is called the reflection coefficient, and it is defined as follows. So the squared reflectance factor, and we simply have to use the squared argument of the above description. When we design absorbers, we are interested in exactly the opposite. So the question is, what is the energy that is absorbed, which is 1 minus the reflection coefficient, leading to this expression here when we use the reflection factor again. So please note that all those quantities, they are exclusively described by impedance of the fluid and surface. So the density or the speed of sound doesn't play any role here, only in its combined form. That means the product of it, which is the characteristic impedance and all the impedance description of the surface. So far. Now let's come to the other option. Now we have a slightly different situation. That means we have the same solution again for the upper area, obviously, but now we don't have a surface that is defined by one specific impedance. Now we have a second medium number 2 with speed of sound and density 2 and the resulting characteristic impedance. So we have two solutions for the upper and lower area, which are given by those expressions. The first one we know already, and the second one is a new one for the transmitted wave with a different angle given by theta 2. Again, we can use trigonometric functions to express the vector products here of the space and the wave number, leading to the following expression that gives us, they are the same that in the first consideration. This is the same thing for the second wave, and this is just a definition again repeating how is the value of the wave number defined when we use the angular frequency and the related speed of sound in each media. Good. So we use the vector velocity potential again with the related results for the pressure 1 and 2. We use the density 1 and 2 and the related velocity potential. Enter all this in the above equations, and then we have to make sure that the pressure at the surface, again z equal to 0, is exactly the same. And using this we get this equation here, relating those two solutions at the contact surface at 0. So again, this solution is only possible for any possible x if those exponential functions are the same. So we get logically the same reflection factor condition as here above, but we get a different condition related to the transmission. If we consider this to be the same, we have to, this is the refraction thing, and we have to fulfill this condition here. So this product has to be the same than this. And this leads finally to the well-known so-called Snell's law. This is known from optics. And here we see that the angle between the different media are defined or given by, related by the different speed of sound or the different wave speed. This is true for optics. And obviously this is also true for acoustics, because it's also a wave phenomena. So when we use this condition, we can outfactor the exponential function in the equation before, and then we get this relationship for the different amplitudes. So the density, the sum of amplitudes of the incoming reflected waves, and the transmitted wave. Again, we have to fulfill a continuity equation for the velocity. So the velocity on both sides must be similar. We apply again the solutions of the different half spaces using the formulation of the velocity coming from the velocity potential. And when we go through the algebra, we end up with this equation here. So that relates the different amplitudes and the different angles and speed of sounds, and gives us more or less everything that we need to come to a final solution. Again, arranging this, we can also identify the reflection factor, which is the ratio between the incoming and the reflected wave number, and we get this result. Again, it looks slightly similar what we have seen before. The only difference is that we now get a vector, an angle argument, also for the second impedance. If you remember, that was just without any angular dependence. That was the case when we just had defined a surface impedance, which is obviously comes without any angular dependence. So The same can now be done for the transmission factor, which is the ratio between the incoming, between the transmitted wave function here 2 and the vector potential amplitude number 1, and this is the result that we get here. So again, using all the we have impedances are given describing the transmission factor, using the impedances on the angles of all the other solutions. So now again, we would like to switch from amplitude relationship to energy quantities, and if that means we are interested in the transmitted power. So what is the relationship between the incoming irradiated power and the transmitted power on an interface of two different fluids? To keep things simple, we just stay with an orthogonal approach, so theta is assumed to be 0. The incoming wave intensity is given by this equation, what we have learned in the earlier sessions of this lecture, and the transmitted power is given by this expression here. So then just to mention what is A. A is just the surface to get some balance, to get really a power. The other quantities would be an intensity expression. So what is P square? This is given by our famous transmission factor. So that means this relates how the incoming and the transmitted energy follows from the incoming pressure amplitude. And combining all this together, we get this expression for the transmission factor. So it depends on the real part of both characteristic impedances of the fluid plus the sum of the absolute value, squared sum of the absolute value of this of both fluids. In other words, again, the transmission properties and later, as it will be shown, the properties of a coupling loss factor are exclusively determined by the impedances. Again, the density and the velocity doesn't play a big role, except in this case that the velocity, the speed of sound, determines the angle of the transmitted wave. Good. So again, the coupling of subsystems is determined by the radiation impedance into the free field of each such system. Why can we now talk about the radiation impedance? The plane wave variation of an infinite fluid is exactly the same as the characteristic impedance. So again, this is something that we will later derive in a fully different context or in a completely more common generic context. This is the description of the transmission factor or coefficient. It will always remain the same. And this is the first hint for the hybrid formulation of statistical energy analysis. Good. So that's it from my side for this session number 8. I hope you enjoyed it. Next time will be tough stuff because we will go a lot into Green's factor formulation, Green integral and Rayleigh integral. So this gives us, helps us to understand how radiation of complicated vibration structures is given into other fluids, and this will be a longer session definitely for the next time, number 8. Okay, see you and bye bye.